Okay, part two of the artificial superintelligence explosion idea from Leopold Aschenbrenner's Situational Awareness paper. Now, here we're talking specifically about the intelligence explosion part. Intelligence explosion is not a new idea. It's not unique to a small cadre of thinkers in San Francisco. Ray Kurzweil wrote The Singularity is Near in 2005 about that. Werner Vinge wrote The Coming Technological Singularity in 1993. So this idea of a technological singularity where intelligence grows exponentially, that is not a new idea, and there are reasons to think that that will happen. However, Aschenbrenner specifically is talking about a scenario that AI researchers call a hard takeoff, and that's the model in which there is one big artificial superintelligence that is out sufficiently in front of competitors that it can begin to improve itself. That process recursively undergoes a loop, then that intelligence becomes so much smarter that it overwhelms all other intelligence. So that's called a hard takeoff. And here is his scenario where he predicts that in around 2027, when AI begins to perform automated AI research and improve itself. Now, these are orders of magnitude on this graph, so this is already a very significant scaling curve, scaling as quickly as it can. Now, the idea is that we'll have a double exponential. A double exponential is quite questionable, and we'll talk about why. The idea here is covered in the media. There are, for example, there's a book, The Metamorphosis of Prime Intellect in 2002. That's a good book that covers a hard takeoff scenario. The film Transcendence with Johnny Depp in 2014 also covers it. The problem here is that we're in a situation where we have many diverse actors that are close in capability. That's much more common in technology transfer, technology development. And that's usually what you see in everything from nuclear technology to microcomputers. There are many actors at a roughly the same point in technological level that are competing with each other. So it's more like the microcomputer revolution. And it's very hard to have a hard takeoff when you're in an intensely competitive situation. What usually happens is that people are struggling to gain the lead. Models are horse racing to be the best, and there's a lot of competition. So in a landscape where you have multiple actors, a hard takeoff scenario is not a great scenario. The other complication is that tight exponential that would then cause a second exponential, a tight feedback loop, is very difficult to take place. In the real world, which you eventually have to interact with, building, regulation, things like that take time. You can't just iterate on a processor and cause immediate improvement. You reach limitations where you know how to improve them, but it takes time. So you do get an exponential increase in intelligence and compute capability, but that doesn't mean that you're going to have a tight spiral in it. So you're usually limited by the rate at which you can acquire chips or power or other things. And he looks at some of those limitations, but there's other ones he doesn't talk about. So, for example, there are what I call non-obvious bottlenecks, unknown unknowns. And so those are things like strategic planning and execution capability and experience. So you will have models that have the intelligence to solve problems, but they lack other factors and you don't know what those are. We find those all the time, like when we're doing agent research, we're like, oh, this agent lacks sufficient strategic planning capability, or it made too weak a plan and we have to teach it to make a stronger plan, or it needs some tools and it knows how to write the tools, but it doesn't know that it should write the tools. So those are the kind of unknown unknowns that exert drag as you're attempting to improve. So he does identify, and I give him credit for this, that AI research is one of the easiest fields to accelerate because it's entirely virtual. And that's true, and that's valuable, but nonetheless, that doesn't get you out of scaling limitations. And so let's talk a little bit more about scaling limitations. So when you see a scaling curve that is being held over some period of time, that is a very strong predictor. And what it's doing is that curve is factoring in all of the acceleration forces and all of the drag forces. So what is almost certain to happen is that the curve will continue on its trajectory or it will eventually flatten out. And what happens with flattening out is that your external limitations eventually begin to take hold. So you use up all of the immediately available capital or power or land or whatever it is, and then things get harder. So that is generally why an S curve flattens over, and that's the normal thing for an S curve to do. So I get his point that AI research is one of the easiest fields to accelerate. That's a valid point. But nonetheless, it doesn't eliminate all of the bottlenecks. It certainly doesn't eliminate the unknown unknowns. You still have to compete for compute capacity. You still have to make money while you're doing it. It still takes time, even if you've made giant breakthroughs in compute. Deploying them does actually take some time, even not just physically, even if they're just virtual. So I don't see a double exponential, and because there are too many actors, I don't see a hard takeoff scenario having the necessary landscape. So in future videos, we're going to talk about the other main points of his article, which are that the infrastructure push that's going on, the idea that artificial superintelligence capability will evade human control, and finally, the national security implications. So stay tuned.